Hi, my name is Kristen Rollins, and today I want to give an introduction to some gradient descent optimization algorithms. These have applications all over machine learning, and if you're new to this, I hope it gives you a good foundation to jump off from, and if you're familiar with them, I hope this will give you a deeper understanding of how they work. So first of all, what is gradient descent? This is an iterative optimization algorithm used to find the minimum of some function. So you may have seen a graphic like this where there's some sort of bowl shape, and you can imagine dropping a marble from the side of the bowl and letting it roll down and find the lowest point. In machine learning, this is used to minimize what's called a loss function, and other names for that are cost function or objective function. And if you need to maximize it, you can just take the negative of the function and use the exact same process. An example of a loss function is the sum of squared errors, which is what you're trying to minimize in linear regression. So what is gradient itself? When you think gradient, you can just think derivative or slope in vector form, and this is the notation. So for some function j, if it's differentiable at some point theta, the gradient is denoted by this inverted delta symbol. And you can use any letters or symbols for the function and the data points. I just want to be consistent and use this j and theta today. And again, the gradient is a vector pointing towards the steepest increase or steepest ascent, and its magnitude is the rate of increase in that direction. So if we're looking at a point down here, the slope is a lot steeper, and so the gradient will be a longer vector, whereas up here, the slope is gentler, so the gradient will be a shorter vector. And to reach a minimum, we'll need to travel in the opposite direction of the gradient, since the gradient itself would lead us to maximum values. So the gradient descent algorithm is pretty simple. You just start by initializing the theta parameters to either 0 or some other random values. Then you'll repeatedly update the parameters until convergence, which can be done in several ways, either when the gradient gets close enough to 0 or when it has stopped making big enough improvements, or you can just simplify it and run it for a set number of iterations. So we have this vector of parameters being updated, and we'll subtract the next quantity because we're looking for minimums and want to go in the opposite direction of that gradient. And this alpha is called the learning rate or step size, which for now we'll think of as being some fixed value. And then we have the gradient of the loss function, which is just calculated with partial derivatives. So I want to talk about the learning rate for a bit. It's definitely important since if it's too large, then it can cause the optimizer to never get close enough to the minimum, just bounce around it, or even diverge and lead the algorithm away from the minimum. But since it's known as the step size, it kind of sounds like we'll be going a fixed distance every step, but it's actually multiplied by the gradient, so it'll really be a distance proportional to the length of that gradient. So this is more of a problem in this kind of situation where it's going along the same distance every time because the slope is the same this whole way, but it gets here and it has no idea that the minimum is approaching, so it just jumps over it and it'll have a hard time finding the minimum. So the algorithm does better when it has a nicer loss function where the slope is decreasing as it gets closer to the minimum. So it takes smaller steps each time and will find that minimum. Here I just want to show something called a gradient field, which I haven't really seen much in a machine learning context, but I think it's useful to help visualize what's going on. So on the right is the function in 3 dimensions, and the gradient field on the left represents the gradient vectors at all of the points, and it's in one lower dimension. So the algorithm starts at some random point, finds the gradient, and makes a step. And it keeps repeating with only this 2D information until it finds where the gradient is 0. Now I want to go through an example using gradient descent with simple linear regression. In practice, we wouldn't use gradient descent here because there is a closed form solution, but I think it's helpful so we're more confident that it'll work in situations where we don't know the optimal solution. So first we have this simple linear regression equation with the intercept and slope. We'll also use the cost function of 1/2 mean squared error. We're including 1/2 term just because it makes the derivative calculation simplify more, and it doesn't change where the minimum value occurs. So our goal is to find these slope and intercept parameters that minimize our loss function for a certain data set. So we also have these update rules, and if you remember the original equation, it looked pretty much the same, but now it's broken into 2 equations, one for each of the parameters. And this gradient is broken into the partial derivatives, and we can go through and derive these, but this is what we will end up substituting in. So for this sample data set, the true slope and intercept calculated with ordinary least squares is 1.28 for the slope and 9.9 for the intercept. And when we use the gradient descent process to try to find these values, in this example the slope got pretty close and the intercept not as close, but maybe that's not as important to us. So this could be refined with more sophisticated convergence rules or adjusting the learning rate. But this shows how it gradually finds a solution that's close to optimal and still very useful. Now let's look back at the partial derivative equations that we had. So here we're evaluating the error, or the distance between the actual data points and the predicted data points for all of the m points. In the example before, we only had to touch like 100 points, but if we have a huge data set, this can get really computationally expensive and restrictive. So at some point, someone had the idea of estimating gradient from just a sample of the data points. And it turns out that this actually works pretty well. And this is known as mini-batch gradient descent, where we take a random subsample of size n and just estimate the gradient. So instead of iterating through all 1 through m data points here, we'll only have to check a smaller number of values, the big N mini batch size. So this is an unbiased estimator for the full gradient. And by unbiased, this just means that it doesn't consistently over or underestimate the value of the gradient. So for the size of the mini batch we decide to use, there's obviously trade-offs. So if we decide to take a larger subsample, this will get closer to the actual gradient, but will be much slower. And if we take a smaller sample, the gradient estimate will be worse, but it can get really fast. And when we take this to the extreme and just use a mini batch size of 1, we call this stochastic gradient descent. The name sounds fancy, but just remember that it's only using a single data point each time to estimate the gradient. And mini-batch and stochastic gradient descent can have an advantage due to taking random samples, since it can help get out of local minima when we really want to try to find the global minima. And there aren't really proofs for this, but we've just seen it work in practice. Now, stochastic gradient descent is fast and works well in a lot of situations, but there are some cases where it struggles, such as navigating ravines, getting stuck in saddle points, or when the data is really sparse. So looking at these ravines, this is known as pathological curvature, where one variable is increasing faster than the other, like in this picture. So in this case, if the algorithm is at this point A, it sees that it's really steep in the W1 direction. So it thinks the minimum is in that direction. But really there's another wall there, so it's going to jump back and forth and go much slower than the optimal path of straight down the middle. So one solution would be to take the second derivatives at every point to figure out how fast the gradient itself is changing and then go in the best direction. But this would require calculating Hessians, which can be really computationally expensive if you have a lot of parameters. So an easier and faster solution is to incorporate something called momentum, where we build up previous values of the gradient and determine the best direction that way. So these formulas look pretty similar to before, but they just incorporate that extra buildup of gradient values. And finally, there's a lot more optimization algorithms out there, and many of them have what's called adaptive learning rates. So instead of a single learning rate, there's a different one for each parameter, which is especially important if the variables aren't on the same scale. So some examples are AdaGrad, which determines learning rates based on sparsity. RMS prop uses a more complicated way to incorporate the previous gradient values. And Atom is a popular one that combines both RMS prop and momentum. These all have their own advantages in various cases, but currently Atom is pretty much the default used for most deep learning applications. So there's lots of these optimizers out there, but most of them have a foundation that builds off the basic gradient descent algorithm. So I hope this has given you a foundation to dive deeper into those algorithms if you're interested. So I hope this was helpful, and thank you.